Hello, Maurits here, and welcome to this video on how to find the area under a curve. We will first look at a theoretical way to do it, and then we will turn that into a practical way to do it, and you can see what the connection is to the previous section. So the problem we have at hand is that we will have some kind of function, f of x, and we want to find the area between the x-axis and that curve. So this is the area we want to find. And the question is how to find that area. An approximate way to find that is to split this area into little stripes, something like this. And each of these stripes will have the height corresponding to the function value at the beginning of that times the width of it. So let us give these points some names. We call this x0, and then we have x1 and so on up to xn. So x0 is a, and xn then in the end is b. Then each of these areas, let them call them delta a, will be approximately equal to the height at that point. This is, say, xr, so f xr times the width, and let us say that each of these has the width delta x. The approximate sign here is because we have this little part that we haven't accounted for. So if we add up these little areas, so I will add them all up. I will write the sum as r goes from 0 to, and not including the last point, because think about this, the last stripe will start at the point before the last xn, so that will be up to n minus 1 of our f of xr times delta x, and that will be approximately equal to our area. If we make the stripes narrower and narrower, we should get a better and better approximation. The reason for that, let's have a look at this little part here. The reason for that is that if this is the curve, and this is the top of one of the stripes, we can see that the error is now this part here. But if I split this in, say, 2 parts, then the error is just this. So the error has decreased. If we split this in even more parts, then the error will be even smaller, and it will approach 0 as we continue. So we could say that this seems reasonable, that if you take the limit of this as the width of our areas will go towards 0, in other words, the number of areas will go to infinity, then the limit will be the area we search for. We will have a short form of writing this and another form to write this. We'll use this elongated s. That is basically the summation of stuff, the sum of stuff. And we say that we want to sum from a to b of our function. And as we did with the derivatives, when we took the limit, we change our delta x to dx. We do the same thing here. So we write dx. So this, we can say, is just another way to write all of that. And we have a name for this. We say that this is the integral of f of x with respect to x, or dx, from a to b. That is a way to express this. This is a particular type of integral which is called definite integral. We will look at other integrals, and the word integral here comes from the word to integrate, and to integrate is to assemble, put together, or make something be part of a whole. That is basically what we do here. We add up a lot of small values to get the total value. This seems all nice and dandy, except for that it's not practical at all. So how could we make something practical out of this? Let's try. So yet again, we look at the problem. We want to find the area from some value A to some value B. Say we have found the area up to some value x, so this area here, let's call that A, will now be a function of x, because if we move the x value to the right, the area will get bigger, and it depends on where x is. And as we move this, we will add a little area. And yet again, as we said before, this area will be the height of the function times the width, and say we have moved this the distance delta x, so our little area will be approximately equal to f of x times delta x. Yet again, the approximate value, because we have a little error up here. Now let us divide through by delta x, so we get delta a over delta x is approximately equal to our function value. And then let us take the limit as we did before, as delta x goes to 0, so we take the limit as delta x goes to 0 of delta a over delta x. And as we take the limit as it approaches 0, then the error will approach quicker, 0 quicker, so we can say that this is equal to f of x. But if we look at this side, we recognize something here, right? That will be a derivative, a rate of change of something. The very definition of derivatives is that we take the limit as the denominator goes to 0 and see what happens. So I can say that this is equal to dA dx. But wait a minute, if we know that the derivative of the area with respect to x equals our function, and we take the antiderivative of this, I should get the area. And by the way, that this is reasonable, this formula here, that the rate of change is proportional to the function. If we look at the original problem, we can see that makes sense, right? The rate of change of the area as we move the point x should be equal to the function value there, since we multiply f of x by delta x, right? So it makes sense that the area will grow in proportion to the function value at the point. Anyhow, back to this, we saw that we had f of x equals to dA dx, and we could reason that if we take the antiderivative of this, we should get the area in some way. So to find the area, we should be able to just find the antiderivative of x plus some constant that is depending on where we start. We'll see an example of that in a minute. So it seems to be possible to find the area using antiderivatives. Let us check if this is true. We should take a simple example where we know the answer to see if this makes sense. So I will take my function y equals to f of x and make a very simple one. So I will take f of x equals to x. And we want to find the area from 0 to some value x here of this triangle. And the area is, of course, the base, that is x, times the height, that is also x, since our function y is f of x is x. So the area here will simply be the base times the height, that is x squared, divided by 2, since it's a triangle. Okay, so let's try to use the method we had over here. So I will write f of x, that is x equals to this. And we take the antiderivative of this, so that should give us that the area equals the antiderivative of x, and that should be x squared over 2 plus c, right? But if x is 0, We are over here. The area should be 0 since we basically don't have a triangle, which means that the area is 0. And if you plug in x is 0 to our function over here, we have that a is c, so that means, in other words, that c must be 0, and we finally have the area is x squared over 2, exactly as we already knew. A bit strange way to find the area, but it seems to work. In the next video, we'll look at this in more detail, and we'll also put all of this together into something called the fundamental theorem of calculus. So over to the next video.